Now let's look at this special quantity here. It's a constant. When we are going through our data for all the categories, the category, the parameters, these M and N, two important parameters related to the data in all the categories. When those two parameters, they vary for all the categories, but the sum of those two parameters is a constant, always constant. So that quantity, that important quantity, so we want to give a special concept, because we will use this concept in our problem solving. We will use it as the insight of our problem solving. It's important. Okay? So the quantity, that quantity, okay, special quantity. So we give it a name, invariant. So actually, so invariant here. Invariant. It never changes, but it is hidden. It is hidden. Okay? You need to discover it. And it is not easy to discover it. So here, we discover it. Okay? But for the general question, some relatively hard questions, we really need to do some deep work to discover this quantity. All right, so understand the role of this invariant. Okay, so what's the role? Usually provides a critical property inside of the problem. So this property can help us keep track of the data. Because sometimes it is not easy to control the data. So data in all the different categories, how do you control the data in all those categories? So this invariant concept gives us a rule, an important rule to control the data, keep track of the data. Okay, right. Here I want to use a simple example to show how to keep track of the data. So give you some impression on its importance. All right, let's consider a generalized chessboard. So let's make a 100 by 100 generalized chessboard. Very large. So definitely we won't play chess on that big chessboard. But we can do the counting, right? We want to count how many squares of different sizes on this 100 by 100 chessboard. Grid, actually. It's not a real chessboard. Okay. In this big chessboard, I want to ask you one question. How many squares are of the size 37 by 37? Only one category. Okay? 37 by 37. One category. I do not need you do the counting on all the categories. Only one category. So how many squares are of the size? So when we answer this question, so remember the definition of the invariant in our previous standard chessboard invariant, and you need to interpret this line Why it is a 9? Okay? Why it is a 9? Yeah. Because the side of standard chessboard is 8, right? 8 units. 8 unit squares. 8 units. So 1 plus the side number. The side number is 8, so 8 plus 1. Okay? All right. So that's our previous example. Now we need to apply that understanding from the standard chessboard to this generalized chessboard. The size number of the generalized chessboard is 100, right? Yeah. The size number 100, the side number 100 units. 100 units, side number. 100 plus 1. Yeah? Yeah. So the same way to derive the invariant concept. We want to get that concept. Yeah. So for this new question, the invariant should be m plus n equals 101, right? Yeah. Yeah. So our invariant m plus n equals 101. Yeah. But the m number is 37, right? Can you find the n number? Right? Yeah. Subtraction. Okay? Yeah. So you can easily find that n number. So you can get your answer 64 squared. 64 squared. Think about, without this invariant concept, it may not be easy to get this 64, right? Yeah? Yeah, because it's hard to do the counting, you know, with the specific work. Yeah, because in your mind, you get lost. When you do the counting, you will get lost. It's hard to keep track of the data. Yeah. But with this invariant concept, we can keep track of the data easily, right? M plus n equals 101. That's the way we keep track of the data. Okay? Yeah. Yeah. Think about that concept. All right? Yeah. All right. Next. Yeah. 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 For some of the questions, it is really hard. But if you can find it, so then it's a big important step to solve the problem. Yeah. All right. Yeah. So for in our first example, so I want to emphasize the importance of this concept. Then we need to find the answer, yeah? Because now we are ready to get a final answer. Okay, all right. So for the number of squares, yeah, because add, you know, subtotal, all the subtotals. So we want to get a total. Okay? Yeah. So this number, so we can find the final answer. Yeah. Yeah. Do further thinking. Yeah. Because this is just a special example. Yeah. If we generalize this problem, yeah. All right. A more general question. We want to count the number of squares in n by n chessboard. Yeah. N can change. N by n, generalized chessboard. Okay? Yeah. That, based on our understanding, yeah, so we should do the summation on these consecutive squares. Yeah. There is a formula. There is a formula, summation formula. Yeah. Yeah. From your discrete math. Discrete math. You have this formula, yeah. Right? Yeah, because in your discrete math, you have some important summation formulas. The first summation formula, yeah, Yeah. The exponent number is 1, the summation of the consecutive integers. 1/2 times m plus 1. Okay? Yeah. The first summation formula. Second summation formula. This one. Okay? Yeah. Third, there is another summation formula. Okay? Summation of consecutive cubes. Okay? Cubes. Okay? Yeah. Okay? Yeah. Becomes harder and harder when you increase the exponent numbers from 1, 2, 3, becomes harder and harder. But this one, okay, this number, square of that number, okay, square of 1/2 n times m plus 1, square, see, see, square of this number. Interesting, right? Yeah. That's enough. Yeah. So the higher becomes really complicated. Okay. Yeah. So we only needed these 3 summation formulas. Yeah. Okay. All right. Yeah. All right. Yeah. So we finished the first computing question. Yeah. First example. Yeah. Yeah. Then our second example, I want to talk about 8.2, prime factorization. Prime factorization. All right. Yeah. Here, let's look at our problem number 2. How to do prime factorization. Okay. Given a positive integer n, how to represent it as a product of prime numbers. That's the prime factorization. Okay. All right? Yeah. So here the reference. Yeah. 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 Very late. Yeah. But it's very easy to understand the question. Okay. Yeah. So that's why I put it here. Yeah. Analysis. Let's understand the problem. First, let us understand the prime numbers, definition of prime numbers. Yeah. So you know it, but here, let me give you a, review a little bit. A prime number is a natural number. Natural number? You know natural number? Okay, all right. Greater than 1. Yeah. We do not include 1. 1 we do not treat it as a prime. 1 is unit. Unit. We do not treat unit as a prime number. Okay? So we exclude the unit when we talk about prime numbers. Okay? That has only 2 factors. 2 factors. 1 and itself. Okay? 1 and itself. 2 factors. Yeah. So example include 2, 3, 5, 7, 11, and so on. Only 1 and itself, 2 factors. Yeah. A composite number is a natural number greater than 1. That is not prime. No. Composite number. No. Not prime. That means more than 2 factors, right? Yeah. Composite number greater than 1, that has more than 2 factors. Composite numbers. Okay, all right. Yeah, yeah. All right, so the definition of these 2 types of integers, positive integers. All right. Then, yeah, so for some understanding question here, is it true that a given number, is it true that for a given natural number starting from 1, right? 1, 2, 3, So we call those natural numbers. Yeah. Not including 0. Yeah. Natural numbers, we do not include 0. Okay? Yeah. All right. Yeah. Yeah. All right. Natural numbers. If it is not a prime, look at if the statement, because it is a question. Okay? Question. So I ask you, if the statement, is it true? Yeah. If, for a natural number, if it is not a prime, then it must be a composite number. Is it? Yeah. For some simple understanding question. If it's not prime, then it must be a composite number. Is it true, the statement? Right? Yeah. Pay attention to the details. Pay attention to the details. Yeah, some question. Yeah. So you really need to be very careful when you read a sentence. Yeah. Look at the 1 here. What is 1? Look at the 1. Unit number. Unit number is not a prime, right? Unit number is not a composite, right? Yeah. So it's false because there is a counterexample unit number. Okay? Yeah. Yeah. So that's why the statement is false. Yeah. All right. For a given natural number, how to determine if it is a prime? Yeah. So that's our key question. Yeah, because we want to check, given arbitrary number, we want to check if the given number is a prime or not. So that's the, basic question in number theory. Yeah. So let's look at this question a little bit. We need to do factorization. Okay? Yeah, because if you get a trivial factorization, yeah, because 2 factors, 1 in itself, it's a prime. But if you get a non-trivial factorization, you have more than 2 factors, it's not a prime. Okay? Yeah. But you need to do factorization. Yeah. So that's why we need to solve this prime factorization problem. All right. How to do factorization? We need to look at the details. Now, let's do some analysis. Basic operation. Because the factor, we know the meaning of factor, right? The concept, factor. Now, so let's start with the factor concept. And if we can represent the given number n as a product of 2 factors, A and B, 2 factors. Factorization. One particular factorization here, for n, we try to get, because we use this factorization to check if n is a prime or not. Try to get. When we do factorization, we want to see if it is possible to find 2 factors, A and B satisfy this inequality, 1 strictly less than A, less than equal to B, strictly less than n. If we can find such A and B, then n is not a prime, right? Yeah. If it is successful, if the first step, this step, if it works, then non-prime. Yeah. N is not a prime. Okay. Yeah. Right? Yeah. Yeah. Right. Otherwise, if it's impossible, so you try very hard, all the possibilities you try, all fail. Okay? All fail. Then you have a final conclusion. Your conclusion is n is a prime. you couldn't find such A and B factors, you can make a conclusion and is a prime. All right? The main steps now, so we can look at the main steps. Right. Determine A and B with this inequality. All right. Question: how to resolve the uncertainty? Yeah. So here, there are a lot of uncertainties here. Yeah. Yeah, because how to choose A's, how to choose B's. So many ways, different ways, uncertain. So we need to work on the uncertainty between these numbers, A factor, B factor. Okay, all right. So here, our understanding in problem solving, there is one important view in problem solving regarding uncertainty concept. How to handle the uncertainty. Because when our data contains a lot of uncertainties, we need to find some efficient way to handle the uncertainty. Okay, all right. So the goal, make it certain. That means we want to reduce the uncertainty, right? Yeah. Uncertainty is not friendly, right? Yeah. Make it harder, make our problem harder. So to make it easier to simplify our problem, so we want to reduce the uncertainties. Yeah. Yeah. So the idea, reduce the uncertainty by exploring the properties. If we can discover more and more properties, then we can apply those properties to reduce the uncertainty. So that's some common step in problem solving. All right, here. What properties can we find for A and B? Yeah. Yeah. Because we want to reduce uncertainties. So we need to find some properties to help us reduce the uncertainty. Yeah. All right. Yeah. If we cannot find any property, no property, then what's the consequence? No. Because sometimes we may not be able to discover any properties, right? Yeah. Yeah. If we cannot discover any properties, what's the consequence? Yeah. Yeah. That means you cannot reduce uncertainty. No useful properties can be applied on your data. You cannot reduce any uncertainty. So the consequence is, yeah, no consequence no uncertainty reduction, right? Yeah. So then the consequence is, as a consequence of this fact, okay, this fact, you need to try all the possibilities. Yeah. Because no uncertainty reduction, you need to exhaust all the possible cases. That's a lot of work. That's a lot of work. So you need to exhaust all the possibilities. Too much work. Why too much work? Because you cannot reduce uncertainty. If you can reduce uncertainty, then you do not need to do that much work, right? You only need to do part of the work. Yeah. Yeah. So that's the logic. Okay. Yeah. All right. 8.3. Now, I want to introduce some ancient algorithm. This algorithm is very old, ancient Greek algorithm called the sieve of Eratosthenes algorithm. Yeah. Sieve. Yeah. Very simple. So ancient Greek people, so they discovered this simple algorithms to find all the primes. Yeah. All right. So let me describe this simple algorithm. All right. Problem solving. How do I answer the? Yeah. I mean, so here, because when we look at the, the solution of this problem, prime factorization. So we want to understand this uncertainty better. Certainty reduction we want to do. Basically, we want to do uncertainty reduction in this problem solving example. Basic operation n equals a times b. Two factors. All right. With. So we work on the data with this condition. All right. Yeah, so here I just repeat our, our view from the previous slide. All right. How to exhaust all the properties. Yeah, because if you cannot discover any problem, you need to exhaust all the possibilities. So now we answer this question: how to exhaust all the possibilities, all the cases. All the cases for A-B pairs. We consider A-B pairs, right? Yeah. A pair of positive integers. Yeah. We want to try all the possible A-B pairs. All right. Range of data. So let's list all the cases. All right. Range, yeah. For A and B, the A and B we choose from this range. Yeah. Because 1 excluded, strictly greater than 1, so the smallest number we can choose for A, that's 2. B greater or equal to A, yeah, okay, 2. The upper bound, B strictly less than N. So the largest possible number for this B, including A, is N minus 1. That's the range we can choose. A-B pairs. All right? Yeah. Now, let's try to list all the possibilities, all the cases. The first pair, 2 and 2. Yeah. A-B. Yeah. B equals A. Yeah. Smallest possible A, smallest possible B. So 2, 2. Okay? All right. Next one, 2, 3. Yeah. So we fixed A, so we increment B, and so on. Okay? All right. That. So 2, N minus 1. All right? Yeah. So the first round. Second round, we increment A number. We get a 3. 3, 3. Yeah, because B greater or equal to A, so the starting point for B also 3. And so on. The second round, 3, N minus 1. Next round, and so on. The last pair, N minus 1, N minus 1. Okay? So that's all the possibilities for A-B pairs. Yeah? Because we cannot reduce uncertainty, right? Yeah. We couldn't discover any useful properties at this point. What should we do to solve the problem? We need to do experiments on all the possible pairs, right? Yeah. For each pair, we take the product, A times B for each pair, and compare it with N. Are they the same number? If they are the same, we get a factorization, right? Yeah. So for each one, yeah, we take the product, do the comparison, then make conclusion. But we need to complete. Okay? Either we are successful. Well, because when we do the comparison, if they are the same, we can make conclusion, right? Yeah, it's not a prime. Yeah. If they are the same, we can make conclusion. They are not a prime, or n. Yeah, it is not prime. N is not a prime. Then we can stop. Yeah. Yeah, because what we are doing, we want to check if n is a prime or not. We can stop. Okay? But if we complete all the testing for all the pairs and still fail, so we can make our final conclusion, it's a prime. It's a prime. Because no such AB pair can be found. No such AB pair can be found, so the conclusion is n is a prime. That's the, that's the algorithm, but this algorithm is not very good, right? Yeah. Because you work on all those possibilities. You cannot do uncertainty reduction. Yeah. So this method, later we call it the brute force method. Yeah. So this method is the brute force method. Yeah. It is the method, right? The brute force method. Brute force method. Okay? Yeah. Brute force method. Yeah. All right. Total number of pairs. Yeah. We need to count. Total number of pairs. Yeah. Yeah. Take summation. 1. So this last one. Yeah. Yeah. 1. Okay? Yeah. Then the next, next round. 2, and so on. Yeah. Yeah. The first round, number of pairs, n minus 2. Okay? Yeah. So the total, yeah, we have the summation formula, remember? We have the summation formula. So we apply our summation formula, 1/2 times n minus 1 times n minus 2. So we need to do this many multiplications and comparisons. If we do the testing on all the pairs. Okay, a lot of work. That's a lot of work. Okay, all right. Yeah, but this is the brute force method. All right. Yeah. But the next we want to, yeah, we're not satisfied with this brute force method, right? Yeah, too much work, not efficient. We want to do better than that. We want to do better than the brute force method. Okay? All right. Yeah. All right. All right. Yeah, so here. Next, yeah, because I want to talk about that sieve algorithm. Sieve of Arretto-Things algorithm. Yeah. So in that sieve algorithm, in this list, yeah, so from 2 through n minus 1, we need to separate primes from composite numbers. Because our interest is at the primes, not composite numbers. So we want to throw away the composite numbers. And we want to keep the primes for the sieve algorithm. Yeah. All right. Yeah. What's the idea, basic idea? Okay. Yeah. All right. All right. Yeah. So here, I'm going to do prime center. Yeah. So, yeah, because this n we can change, right? Yeah. So here we talk about the general method. Yeah. Find the primes in the above range. Okay, all right. Yeah. Yeah. So let's do observation. Yeah. To form a composite number, the form, yeah. So, because we want to throw away composite numbers. Yeah. Yeah. And because prime numbers are harder to detect, right? Yeah. Yeah. Think about, there are two types of numbers. In this range, there are two types of numbers, primes and the composite numbers. Yeah. In these two types of numbers, which type is easier to detect? Okay? Yeah. Composite number is easier to detect. Prime numbers harder to detect. Okay? Why? Yeah. Why prime numbers harder to detect than the composite numbers? If you look at the previous slide, okay? The previous slide. To detect a composite number, if we can find one pair, AB pair, the product of AB equals n, we can make conclusion it's a composite number. Yeah. Well, you only need one experiment. If one experiment works, you can make your conclusion for the composite numbers. But how about prime numbers, primes? You need to do all the possible testing, right? And when you fail on all the possible experiments, you can make conclusion for prime numbers. That means you need to do more work on prime testing than composite number testing. More work. Yeah. All right? Yeah. So after we do this kind of comparison, okay? Yeah. We make our conclusion. It is easier to handle composite numbers than handling primes. Then, when we work, because working on composite number is easier, then when we solve the problem, we should start with the easier case, right? Yeah. We should start with the easier case. You should not start with harder case, right? Yeah. Yeah. All right? Yeah. People always start with easier cases. Okay? All right. So based on that understanding, analysis, yeah. That's why we work on composite numbers. Easier. Yeah. All right. Yeah. So n equals b, a times b. Composite numbers. Okay? All right. Yeah. Yeah. All right. And, we interpret composite numbers as a multiple. Yeah. How do we understand the product of a and b? Yeah. So here, we spend some time to understand the form of n. If it is a composite number, it takes this form, right? Yeah. It has the product form. Yeah. Then, when you see this product form, we have different ways to view this form, right? Yeah. So when you see some object, yeah. Here, that product is the object. So we're working on this special object. When we look at one object, do we have multiple views on this object? Yeah. We can take different views on the same object, right? Yeah. So here we want to change our view. In problem solving, take different views on the same object is very important. Sometimes we need to change our view. Change our views. Here, we use a different view. How do we view this product? Okay? How do we view this product? Product, we know, it's a simple structure product. But here we view this specific product as A multiple of B. Okay? So A multiple of B. Yeah. That's the way we view. We change the view. Okay? A multiple of B. A multiple of B. Yeah. Or B multiple of A, right? Yeah. A multiple of B or B multiple of A. That's the product. Yeah. Yeah. But the A multiple of B, we can fix this A. Fix this A. Then we look at all the multiple of A, or yeah, we fix A, all the multiple of A. See? See? All right? Yeah. So here. So taking some special view is very important in our understanding. Yeah. So here, we use a, this view may not be very natural, right? Sometimes the view may not be very natural, yeah, but we need it. Yeah. Here we need the special view. B multiple of A, yeah? Because there are two ways to view it. Sometimes A multiple of B is better. Sometimes B multiple of A is better. Right? So we have different views. Yeah. Okay, all right. Yeah. So now we want to apply this new view to help us remove all the composite numbers. Now, remove all these product forms in this list. In this list. Now, if we cross out all the composite numbers, the remaining numbers are primes. That's simple. All right. Yeah. The property. Yeah. 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 So we did analysis. Okay. All right. Strategy. Okay. Now, based on our understanding, okay, yeah, all the understanding here, now we come up with some strategy for our problem solving. Remove all the composite numbers. Then the prime numbers remain. So this strategy is the basic idea of that sieve of things. Okay, yeah. So next, let me talk about the sieve algorithm. Yeah. All right. Sieve of things. All right. Yeah. So the Greek people, yeah, ancient Greek people, so they work on a table on sand, okay, ground, yeah, on ground, okay, all right, in this way. So they organize the data, yeah, so they need to organize the data. Well, yeah. So ancient people, they know they need to organize the data, okay, all right. So they need to arrange the data in a nice way, okay, not a messy way. Okay? Not a messy way. Okay? All right. Yeah. So targeting the composite numbers. Yeah. Okay? Not targeting primes. Primes too hard to work. Yeah. Composite numbers much easier to work. So they target composite numbers. But how to organize composite numbers? Yeah. Composite, you need to organize them, right? Yeah. They use different categories. Yeah. They put the composite numbers in different categories. Yeah. So, what category? The first category, multiples of 2's. First category. Second category, multiples of 3. And so on. Multiples of 5 next. Yeah. So here you can see multiple of a prime number. 2 is a prime number, right? 3 is a prime number. The next multiples of 5. Why not multiple of 4? Because multiple of 4 belong to multiple of 2, right? Yeah. So we won't have multiple of 4s. So we have multiple of 5 and so on. Okay? All right. So that's the characterizations. So they organize their data in this large table to work, to do the work. Okay? Yeah. To do the work, see work. Okay? All right. First, they cross out all the multiple of 2s. So they scan the sequence from beginning to end. When they see multiple 2, cross out. Okay? Yeah. The first round, cross out all the multiples of 2s. Yeah. But not good enough. The second round, cross out multiples of 3. But when you cross out multiple 2, don't cross out the first one. 1 times 2, right? Do not cross out 1 multiple of 2, okay? 1 multiple, it's a prime. Okay, don't cross out 1 multiple of 2, okay? Starting from 2 squared, 4. 2 squared, 4 to do the elimination. All right. Next round, when you cross out multiple of 3, do not cross out 1 multiple of 3. You cross out, yeah, because second round, okay? Cross out 3 squared, starting from the first one. 3 squared, okay? Yeah. 3 squared, okay? That multiple of 3, okay? Second round, okay? Third round, you need to cross out multiple of 5, but starting from 25, 5 squared, 25. Yeah? Because before 25, you do not need to worry, okay? The first 2 rounds already eliminate all the composite numbers before 25. Okay? Yeah. Why? Yeah, later we will see. Later, because when we write the algorithm details, we need to go through the algorithm detail. So we will see why. We do not need to worry about the numbers before 25. Okay? So the third round, crossing out, starting from 5 squared. 5 squared, third round. Okay? Multiple of 5. Okay? All right. Fourth round, multiple of 7. But the starting point is 7 squared. 49. 7 squared, 49. That's the first one to cross out for the fourth round. Okay? Yeah? Yeah. All right. After 4 rounds, you can stop. You don't need to, here, to find the primes within 100. Here I use example, within 100. You only need to do 4 rounds crossing out. 4 rounds, good enough. After 4 rounds, elimination, all the remaining numbers are the primes. That's the sieve of errata things. Ancient Greek algorithm, sieve of errata things. Okay? Yeah. All right? Yeah? Yeah. Why it is correct? Yeah. So I need to explain why it is correct. Right? Yeah. So, yeah. Not hard to understand. Not hard to understand. So, all right. Yeah. So here, we want to understand better. Yeah. How do we know that algorithm is correct? No. So when we want to check if this algorithm is correct, first, we want to make sure after 4 rounds of eliminations, all the composite numbers should be eliminated. That's the first thing we want to make sure. Second, we should not eliminate any prime number, right? Yeah. So we don't want to eliminate any prime numbers. Okay, yeah. So, all right. The first question, why it is enough to only do eliminations for composite number in 4 rounds? That's enough. We don't need to do 5th round. If you do 5th round, you cannot eliminate any composite numbers. Because no composite numbers remain. After 4 rounds elimination, you have all primes. You don't want to do, nothing, right? Yeah. Yeah. So let's look at the structure of composite number. This is structure of composite number. Okay, all right. Yeah. Yeah. Consider the range of A. Yeah. So we have 2 factors, A factor and a B factor. First, let's look at the range. What is the range for A? Yeah, we want to examine the range only for A. Here we don't look at B. We only look at the A. Range for A, not B. So what's the range for A? All right. The range for A, yeah, because N equals A times B, and we know B is greater or equal to A. If we replace B by A, then the product becomes smaller. So A times B is greater or equal to A squared. No problem, right? Yeah. That means A squared less than equal to N. A squared less than equal to N. Okay? Yeah, that's inequality. Obvious inequality. That means the lower bound for A factor is 2. Well, still lower bound 2. Yeah. The upper bound won't be N minus 1. The upper bound becomes floor function of root of N. Yeah, because A squared less than equal to N. We take a root, take square root to both sides. A less than root of N, but A is an integer, so we take floor function. So this is the upper bound. This is the upper bound. Okay? This is the upper bound. Upper bound for A, this expression. Okay? All right. This expression. Now, let's look at this here. N equals 100, right? N equals 100. A less than equal to root of 100, that's 10. So you only need to consider A less than 10, right? In this above, this specific example, you only need to consider A less than equal to 10, but we crossed out all the composite numbers. So actually, you only consider prime numbers less than equal to 10, right? Because composite numbers have been crossed out. Composite numbers all gone. Composite numbers less than equal to 10, all eliminated. Okay? So you only look at the prime numbers less than equal to 10. The largest prime number less than 10, it's 7, right? After you do 4 rounds elimination, you already reach the upper bound for A, right? So you can stop, okay? Because you processed the upper bound for A. Okay? No need to look at the numbers higher than this upper bound. No need. Okay? The range for A, this is the range. You only consider A in this range. And specifically, you only need to consider prime numbers in this range. So that's why you only need to do 4 rounds of eliminations. Okay? Good enough for the sieve algorithm. Okay? Yeah. All right. Yeah. So now we have confidence. So here you can see, after this is the problem we discover, right? Yeah. So here, using our understanding for the uncertainty, yeah. Here, do we reduce the uncertainty if after we discover this is the property, right? This is the new inequality we discovered. Yeah. So after we discovered this new property, think about, do we significantly reduce the uncertainty, right? Yeah? So when we do experiments, we only need to do 4 rounds. That's some reduction, right? Yeah? Yeah. So that's some, uncertainty reduction. Okay? Yeah? All right. All right. Yeah. So here, only use the prime in this range. Yeah. So that's the, main idea of the sieve algorithm. Yeah. All right. So next, implementation. Because we need to write program, right? Yeah. So let's see if we need to do the prime factor. Yeah. So here, think about it. So in order to solve this problem, we need to write out the details of the implementation. For coding, we need to specify the details of implementation. All right. We begin with the first number P in the table. P start with this 2. That's P. Okay? Yeah. In the table. And we need to do the eliminations. The first round elimination, declare P to be prime. So that's the prime. When we start, it's a prime. Okay? Declare P to be prime. Then, when we do eliminations, the elimination is related to the P prime, current prime P. Multiple of current prime P. But the multiple, we cross off all the multiples of that number in the table, but starting from P squared. Starting with P squared. Why P squared? Yeah. So you may ask me, why P squared? Yeah. So let me explain another. Why P squared? Why the smallest composite number to start with is P squared? Because when you start with P, that means this P is your A, right? Your A equals that P. Then why P squared? Because the smallest possible B equals A, right? Yeah. The starting point for B is A. When B equals A, B also is P, right? B is also P. A is P, then the smallest possible B also P. So A times B is P squared. Smallest product of AB is P squared. Okay? Yeah, that's why we start from P squared. Okay? Yeah. P squared, all right. Yeah. Then Find the next number in the table after P. Yeah, because after you complete those rounds, right? Yeah. So crossing off, all the composite numbers. The next P, so next number in the table after P, that's a new P, right? Yeah, so we will, okay? So, yeah. Next P, yeah, then, do the same thing. Next P, then next P, and so on, okay? All right. All right, yeah, so that's it. So we will finish this topic next time quickly, but just the pseudocode, okay? The pseudocode part. Then we'll finish. Then we start part B next time on Wednesday. But it's online, okay? Wednesday. So you do not come to the classroom. Yeah, so I will post a Zoom link. So you just connect to my Zoom meeting at the class time.